Hello, Chem 30. We are into week 8. This is without a doubt the home stretch. And with it being the home stretch, we are officially entering our fourth and final unit, chemical equilibrium. Now, I recognize that it is a slightly shorter week with Monday being off. Happy long weekend, by the way, to you all. So there's only 3 podcasts again this week. I think the assignment is a little bit shorter than some. But that being said, we're not building particularly on a lot of past concepts. We're really focused on something a little bit new. So it might take you a little bit more time, a little bit more listening to the podcast, a little bit more of a focus to digest it and to understand it. Now remember, this is the beginnings. We're building off of this. So it's really integral that you have a good foundation for the remainder of the unit to build upon. So please, keep that in mind as you're going. Do not lose steam at this point. I know motivation is hard with distance learning, but do your best, persevere, and we will get through this. All right, so chemical equilibrium, our initial focus is honestly just an introduction to what I mean by chemical equilibrium and how we can determine what the concentrations of different reactants and products are once they reach chemical equilibrium. Ultimately, what equilibrium relates to is the fact that most reactions don't go 100% to completion. That's actually a pretty rare thing to happen. Generally speaking, a lot of chemical reactions are reversible. Now, I'm not saying that they're entirely reversible, that you go completely from products back to reactants or vice versa, but there is a back and forth element to them. I mean, some of this is super familiar already. Just consider formation reactions versus decomposition. Take water. If you form water, you're reacting hydrogen gas plus oxygen gas to form water. Ding, 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 done. While we know we can definitely put water under electrolysis and take that water and decompose it into hydrogen gas and oxygen. Reversible process, folks. Now, when we talk equilibrium, we are focused on this type of a nomenclature for the arrows. So it's not a one-way arrow. It is not an arrow where we have a point on either end. Don't use that. This is what we want, right? It was introduced to you in the past. We're going to utilize it again. We have, therefore, 2 opposing reactions. One of them is going forward. The other one is going in the reverse. And they take place at the exact same time. Now, they're not just taking place at the same time, but the rate is the same. And this is key. The forward rate of the chemical reaction is equal to the reverse rate of the chemical reaction. Now, this isn't to say that it can't favor the forwards or the reverse. It's not to say that there's always identical amounts of reactants and products. All I'm saying is that the reaction rate is the same, which means it's going to reach something that seems a little bit like homeostasis, like a consistency of the concentrations of the reactants and the products, because the rates are identical. Let's explore this further. Now, remember what I was just getting at. At equilibrium, you're going to hear that statement a lot. At equilibrium, at equilibrium. Anyway, at equilibrium, the concentration of every reactant and every product remains constant. Now, I'm not saying they're identical. I'm not saying, hey, if one reactant has a concentration of 2 moles per liter and everything else has that concentration. Not at all. I'm just saying that it stays constant. It's not fluctuating. It's not going up, down, up, down, up, down. The next thing, at equilibrium, all of the observable properties, we call these macroscopic properties, the ones that you can actually visually see. Classic examples would be color, the pH, the pressure it's at, the temperature. All of these at equilibrium are constant. If they're changing, it's not at equilibrium. Next, at equilibrium, we have a circumstance where that equilibrium is considered to be dynamic. And dynamic, by definition, means that it is not stagnant. There is movement, right? So if there is movement, but it's not observable, that means that those changes are occurring at a molecular level, at a non-observable level. You won't see any changes in observable properties, but to be sure, constant changes occurring in the molecules. All right, let's continue on with a couple more characteristics and recap of equilibrium. First things first, you must have a closed system, and you must keep temperature constant. Temperature has an impact on equilibrium. So if you change the temperature of a system, you are going to impact what that equilibrium is. Hence, equilibrium only remains when it is closed, when you're not adding anything, in other words, right? A closed system means that there's no matter going in and out, and when you maintain that temperature. The next thing, equilibrium can be approached from either direction. That's because you have something that is going both forwards and reverse. And not just that the forwards and the reverse reaction are both happening, but they are happening at the same rate. Very, very important. So either direction, closed system, constant temperature, same rate. Focus on those things that I'm highlighting here. Next, equilibrium does not mean, I mentioned this earlier, that all chemicals are at the same concentration. Not at all. The concentrations of all the chemicals at equilibrium are often different from each other, but they remain consistent. For instance, if my equilibrium concentration of hydrogen gas in the formation of water is 1.2 moles per liter, it stays consistent at 1.2. The concentration of the water, on the other hand, might be 3.6 moles per liter, but it consistently stays at 3.6. Alrighty, let's start to do some analysis. Here's the first question we'll go into, and we're going to keep it simple. We'll do a formation reaction, and we're going to form hydrogen iodide gas. The formation of this gas takes place at a high enough temperature that both the hydrogen gas and the iodine is a gas as well. Usually iodide is a solid at room temperature, but we're not dealing with room temperature. Take note, we are dealing with an equilibrium, hence we've got the forward and the reverse arrows both being listed. Now this is an interesting reaction to do. It's kind of a good one because there's actual visual to see this. You can see that we've got one of the gases that is purple, which means if the reaction is favoring, for example, the forwards direction, then you'll end up with the purple color decreasing, disappearing. Vice versa, if you end up with a situation where the reverse reaction is favored, the purple color will intensify. Reactions where color is associated or other observable properties are helpful, right? Because then once that color stays consistent and doesn't change, you're like, ooh, we've reached equilibrium. Anyway, let's keep talking. Now, with this reaction, let's say that I give you a scenario where we're going to begin with the reactants only. Right? So I'm only going to put the hydrogen gas and the iodine gas into an empty flask. And it would look something like this, right? You'd have that purple color showing up. And as equilibrium starts to form, so as those two react together, the purple color is going to slightly fade. Why? Because it's favoring the forwards reaction. It's going to start to produce the hydrogen iodide gas. Is the purple still there? Yeah, it is, which is interesting. How do we know that? Well, we know that empirically. We've seen the evidence in experiments that the purple color remains. So if it's not completely colorless, that means we're not fully to the hydrogen iodide gas. Some of the purple iodine gas, must still remain. Lighter shade of purple. Stays constant once it's at equilibrium. Okay. This is called an ice table. Now, sorry, see I've got a little bit cut off. There's supposed to be a G here, like that. There we go. We take the initial balanced chemical reaction, and ice, and you can see it's in square brackets. That's done intentionally because these are concentrations. The I is representative of initial concentration. So what you start with, the C in the square brackets is about the change that the concentration undergoes, and the E in square brackets is about the equilibrium concentration. Now, guys, you'll notice in the notes that I have a capital M. I did that on purpose, and the reason I did that is so that you recognize these mean the same thing. So that capital M stands for molarity, and molarity is always a molar concentration. Uh-oh, sorry, there we go. So molarity equals molar concentration, and molarity equals always moles per liter. It's just you can use the capital M as sort of a way to shorthand the mole per liter, if you will. It's perfectly acceptable, okay? Alrighty, look at this one. We've got one situation where I get a lot more information, and it's this one right here with the iodine gas. The iodine gas, I'm told that it initially started at 1 mole per liter, and then it finished at 0.2 moles per liter. The key thing for you to notice is the concentration went down. Now, how much did it go down by? This is something that's new, and that we need to look at the coefficients of the balanced reaction to give us an idea of the amounts that these concentrations are changing by. In front of the iodine gas is a 1, right? We don't write the 1, but you bet it's there. And that means that this is going to go down by, how do we show something decreasing? A minus. And it's going to go down by 1x amount. Why a 1? Because the coefficient is 1, right? They match each other. I have an algebraic expression there. I'll show you what I mean. Take a look at that. We have a circumstance where we can see we have for iodine gas 1.00 moles per liter minus 1x will give us 0.20 moles per liter, or you can just use capital M like I said. Well, simple algebra, guys, right? 1.00 minus what number is given, give us 0.2. It ends up being that x is equal to 0.80. I'm going to use capital M here. It means the same thing, moles per liter. So we've just, based upon that one thing for iodine that I outlined in yellow, found algebraically what x will be. That's super useful because from that we can now predict the equilibrium concentrations for hydrogen gas and for hydrogen iodide gas. I'll show you how. The hydrogen gas is on the same side as the iodine, which means they're both reactants. If they're both reactants and one reactant is decreasing, well, the other one must be too because they're reacting with each other. How much is it going to go down by? It has a coefficient of 1, so it's going to go down by 1x. Remember what I already said, x is equal to 0.8. I often with these guys use my calculator for this. If you look on your calculators, you have a button that stores things. So what you could write is you'd go 0.8, and the store button is right above on a TI-84, for example. So then you push store, it puts a little arrow beside the 0.8, and then under mode, so that's right beside the green alpha button, you can see xt theta n, touch that, and now here I'll write it down for you on my page here. What you should see on your calculator is 0.8 arrow x, right? This, I just highlighted yellow. This right here. You got that by typing 0.8 store x, and they have to push enter. If you don't put enter, it won't work. So what you've done now is stored that value, and it'll stay there until you store something different. You don't have to go back and delete or anything. But here's what's useful. Now you can type for hydrogen gas 1.5 minus, and then type that x, the xt theta n. And you'll see in your calculator 1.5 minus x. Push enter, and all of a sudden we've got an answer. 0.70 molarity, mole per liter. Okay, it's still stored in there. Let's move on to the hydrogen iodine gas. This one's a little bit different. If the reactants are going down in concentration, the product must be going up. It's like a seesaw. It's a balancing act. How much does it go up by? Well, we're going up, so we're going to put a plus, and it's going to go up by 2x. Why? Because in the balanced moles, coefficients, it's always double of those two reactants, right? One iodine or one hydrogen gas produces two hydrogen iodide. So if they go down by one amount, the hydrogen iodide gas has to go up by two amounts, 1-to-2 ratio, guys. Okay, so again, I'd use my calculator for that. I stored X in, it's pretty easy math, that's okay. 0 plus, and literally you can type on your calculator 2X, it right away comes up as 1.60 capital M, molarity, 1.60 mole per liter. You've just completed your ice table. There we go. Key thing here that's going to come into play later is you now know the concentrations of each of the different chemicals at equilibrium. Okay, that's important. Now we're going to utilize this and graph it so you can really see how these things are changing. Okay, you all have this graph and the concentrations aren't exact. We're not trying to numerically graph these exactly as they are, so it's just relative. Now, I'm going to do this mostly with highlighters so that you can see. And these are the same colors that I used on the notes. I'm going to start with the hydrogen iodide. Now, before equilibrium, the hydrogen iodide was at 0, right? So that's where we'll start here as well. So hydrogen iodide is down at the very, very bottom, 0. Now, it goes up by a factor of 2. Why? Because of the balanced equation. So when we go up by a factor of 2, it's now in the C part, it's changing. And then once it hits equilibrium, the concentration is again consistent. So it's flat. Again, this is for my hydrogen iodide gas, and it's going up by a factor of 2. Let's do another one. My iodine gas is starting at a higher concentration at 1, so definitely not 0. So I'm going to put it up here just to be relative. And it starts at a consistent concentration, then it changes. And it doesn't go up in concentration, it goes down. It doesn't go down as much as the HI goes up because it's only a factor of 1. But once I get to equilibrium, it's nice and consistent again. It stays constant, right? The system after equilibrium. That is for my iodine gas, and it's going down by a factor of 1. The last one we need to deal with is our hydrogen gas. Hydrogen gas is relatively a little bit higher when it starts, but it goes down by the exact same factor as the iodine, a factor of 1. So I'm going to try to mimic the shape, right? Keep that looking similar. And then once again, it goes nice and flat once we hit equilibrium. And that's our H2 gas, down by a factor of 1. Key thing I want you to notice, the reactants both are going down. It always has to be that. You'll never get one reactant going up and one going down. They're on the same side of the equation. They have to mimic each other in terms of how they change. Vice versa, if the reactants are going down, the product has to go up. Why? Well, guys, it's a conservation of matter. If you are reacting the reactants, they have to go somewhere. Where do they go? Into the product. Okay, let's try another example. Moving on to this one. We're going to form something different here. What if instead of our hydrogen iodide gas, we're forming ammonia? So very simple formation reaction. We take nitrogen gas, don't forget diatomic, plus the diatomic hydrogen gas, balance the reaction. It forms two ammonias. And we know it's at equilibrium. We see those equilibrium arrows indicating that there's a forward and reverse reaction happening simultaneously. There's a bit of information you got about this thing. In this scenario, we have a situation where you're starting with no reactants whatsoever. They're both at 0. Whereas ammonia, we begin with. Now, is it just going to stay as ammonia gas? Because the forward and reverse reaction happen at the same time. So it's going to slowly change the C section until it reaches equilibrium. We have some evidence already. That evidence exists for the hydrogen gas. And the evidence tells us that it goes from 0 to 0.90 mole per liter. In other words, 0.90 molarity, capital M. So it goes up. It goes from 0 to that. So you are adding. How much are you adding? A 3x amount. Why the 3? Because of the 3 coefficient. All right? Simple math, simple algebra. 0.00 molarity plus 3 x's is going to equal 0.90 moles per liter, right? Minus the 0, divide by 3, divide by 3. Man, guys, let's be honest, this is easy algebra, okay? X ends up being equal to 0.30 moles per liter. Why is that so important? Because that X amount tells us how the other reactant and product are changing. How do they change? Nitrogen gas has a 1 in the front. So it is going to increase. Why is it increasing? Because it's a reactant. Hydrogen's a reactant. If the hydrogen increases, the nitrogen must as well. And it's going to increase by a factor of 1x. 0 plus 1x, this is going to be at 0.30 moles per liter. Vice versa, the ammonia is a product. It's on the other side. Take note of that. It has a 2 as the coefficient. So it's going to go down by a factor of 2. Why is it going down? Because it's the product and the reactants are going up. They always have to be opposite of each other. Always, always. So minus 2x. Again, if you want to use your calculator for this, you could. You would type in 0.3, store as x, enter. Now it's put in. Now to do this equation, 2 minus 2x. And we get a total of 1.40 moles per liter. There you have it. There are our concentrations of the two reactants and the ammonia product at equilibrium. Let's draw these again and look at the comparison. Now, we have a scenario once more where something's starting at 0, but it's not singular. It's two different entities. So these are always a little harder to draw. I tend to just draw them over top of each other. My yellow is going to represent nitrogen, and my green is going to represent the hydrogen. So I just draw them right over top of each other. Now, factor-wise, the nitrogen gas is going up by a factor of 1 because of the 1 coefficient. The hydrogen gas is going up by a factor of 3 because of the 3 coefficient. So we can still draw that somewhat relative. So I'm going to show the yellow one going up quite a bit less, right? A factor of 1. So I'd say, okay, times 1, and that's my N2 gas. Vice versa, the one that I did is green, the hydrogen gas is going up by a much higher factor, right? Factor of 3. Flattens out once it hits equilibrium. That's always key to do. And that's the H2 gas times a factor of 3. The ammonia, on the other hand, and I'll do that with the turquoise, the ammonia starts off with an amount other than 0. So just relative, we're going to put it here. And it's going down by not a factor of 3, not a factor of 1, but by a factor of 2. Again, relative, guys. Right? Relative concentrations, not perfect. And this is NH3, that's the ammonia going down by a factor of 2. Once again, notice though, they're opposites. Both reactants are going up, therefore the product has to go down. And vice versa, right? They always have to be opposite on either side of those equilibrium arrows. One more. Here we go. What if a different reaction we're going to deal with, the reaction of nitrogen monoxide gas with chlorine gas to produce our NOCl2. Okay, fine. But what if we have a circumstance where we're going to start with a mix of all of them? We're not going to have only reactants or only products, but instead, here's our scenario. So things change a little now. We have some of the reactants and some of the products. Now, as always, we're going to have one of them that we can analyze. And in this case, it's the chlorine gas. I know how it begins initially, and I know how it finishes. This is already balanced. It is, because of the number difference, I see 2 to 1.75. That means it's going down, so it's going to be a minus. And the coefficient in front is 1, so it's going to go down by a factor of 1. Minus 1x. Determine what x is. 2.00 molarity minus 1x will give us 1.75 molarity. Oh, that's easy math again, guys. X is equal to 0.25 moles per liter. Okay, if this is x, I can now apply that into the other two. If chlorine gas is going down, that means the nitrogen monoxide gas is going down as well. By how much? A factor of 2. So minus 2x. So again, use your calculator if you want, but it's 1 minus 2 times 0.25, easy math, which gives us a total of 0.50 moles per liter. Vice versa, on this side, we've got 2 NaCl2 gas being produced. And if the reactants went down, the product must go up by a factor of 2 because of the 2 that is the coefficient. So 3.00 plus 2 times 0.25 is going to equal 3.50 moles per liter. There it is. There are our concentrations of reactants and products at equilibrium. Okay, let's draw this thing. Once again, your drawing doesn't have to be perfect, but it has to show relatively that the 2 reactants are both going down in this case, whereas the product is increasing in concentration. I'm going to do my nitrogen monoxide gas is yellow. It's starting at a concentration. It's not at 0. I'm going to put it a little bit higher here. Okay, so starting with a concentration, and then it's going to go down by a factor of 2 until it is at a nice, consistent, straight line again at equilibrium. Why is it straight? Because once it hits equilibrium, it is at a constant concentration. That is for my nitrogen monoxide gas, down by a factor of 2. Consistently then, my chlorine gas, another reactant, is also going to have to go down. Now this one's going down just by a factor of 1. So it's still sloping downwards, but not quite as steeply, right? So times 1, a factor of 1, that's the Cl2 gas. On the other hand, the nitrogen and oxygen chloride gas is going to be going up. So it starts at a concentration and then goes up by a factor of 2. Oops, it disappeared on me. There we go. Until it hits equilibrium where it's nice and flat. So times 2 going up, NOCl2 gas. There you have it, guys. You've now drawn and learned about how to do your ice tables. Now, in the homework, it's mostly ice tables. I'm not going to have you do a bunch of graphs. The graphs are important. They'll come back in for us to look at again in the future. But from a question perspective, I want you to focus right now on 1A. I want you to also attempt to do, please, 2A, B, and C. There's a little bit of a twist on A and B. Don't make it harder than it needs to be, guys. It says calculate initial concentrations. Honestly, you could have done that in grade 11, right? That will be Chem 20 stuff. So again, I'll say this one more time. What you do in 2A and B is nothing new. It's Chem 20 stuff. It's just calculating concentrations with a given mass, right? And then the concentration needs to be in moles per liter with a given volume. No big deal. 2C is this new stuff where you got to use the ice tables just like I just showed you. Ice standing for initial concentration, changing concentration, and then the equilibrium concentration. Good luck to you. Feel free to come on Thursday to the optional Google Meet if you got questions that you want to ask.